Hey, folks, good afternoon. Welcome in. Or good morning, sorry. Good morning. Hi, everyone. Hey, Anna. Hello, Kiora. Hello, Kiora. Oh, oh, there we go. Hi, Nathalia. We got a busy day ahead of us. In a couple of minutes, we'll get started. So hopefully more people join because we only have 7 right now, which reminds me, I got to take attendance. Alicia's here. Anna's here. Kiora's here. Maddie's here. Nathalia and Shafak also. And then Dominic's here. Alan's here. All right, folks, welcome. Hello, for those of you just joining. I'm going to try to get as many of these practice problems done today, examples done today, so that way you can get the homework done and dusted. And if you haven't looked at it already yesterday, then for sure, definitely this afternoon or this evening you can, because those of you who I sent emails to about meeting with, my hope is that you checked your GAPS email as for my post this morning. And yeah, if I sent you an email, that means I've scheduled a meeting with you. So please let me know if you can make it. I don't actually think it's anyone here. Yes, correct. So a couple more minutes and we'll get started. Tammy's here. Ashley's here. Emily's here. All right, folks, I'm going to get started in just one more minute because I want to be respectful of your time, and we do not have a lot of time today, but I still want to cover some of the practice examples that we did not get to yesterday. So I'll give everyone one more minute to join in, and then I will get started because we have until 10:45 to get through a couple examples. Jaden's here. Hi, Emily. How's it going? Hi, hello. Hello. That's how I'm going to say that. Oh, Jaden's having trouble joining again. There's 11 Jadens. Jaden, did one of you join, Jaden? Yes, one of you joined. Excellent. My internet is unstable. Yeah, mine was being weird today too. Or was that yesterday? Yesterday when I was watching stuff on the television or Netflix or whatever. So if I leave, whatever, don't mind me. Got it. No worries, Maddie. All righty. Okay, folks. Oh, we got a lot of other people joining. Helen, Arlena, and Han. Helen, Arlena, and Han. Helen, Arlena, and Han. Also, it's super funny that I'm definitely allergic to the sanitizer we use at my work because every time I smell it, my chest burns and my throat gets tight. Oh, dear. Bring your own. Bring your own. Jonathan's here. Catherine's here. Okay, folks, it is 10:20. I'm going to get started now because we have some content that we want to get covered. And as the last few people trickle in, hopefully, you cannot avoid it. Oh, dear. Sanitizer. Oh, that's upsetting. Yeah. So it's like ammonia-based or whatever. Oh, Jesus. Well, you won't be able to sue them if you're long gone. Not long for this world. Okay, your family will. That's true. That's true. That's true. That's fair. That's fair. All right, let's get started, folks. So if you recall from yesterday, we looked at these coin flips as a means to describe how probabilistic chances work when it is a 50-50 chance. And when we combine those two 50-50 chances, what are the odds of getting each of these outcomes? Heads, 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 tails, tails, tails. The same thing from yesterday that we remember learning can be applied to what's called Punnet squares. These Punnet squares are grids that we can create when dealing with genetic crosses. If you recall, genetic crosses are when we deal with two true breeding specimen or species. We cross those two, they share genetics and they create offspring. And we can use Punnet squares to determine the expected proportions of offsprings, of that genetic cross, because it will show us all alleles that are segregated from one another, and they have equal probability of occurring in those gametes. And as a result of that, we know that each parent has two alleles. Like, for example, they can be heterozygous, capital F, lowercase f. They can also be homozygous, dominant, or recessive. And they only give one copy of each allele to each gamete. And we can use that understanding. To use that 50% chance of each gamete receiving either allele. We can use that understanding to kind of describe and demonstrate how those offspring, or the probabilities that offspring will be made a certain way. And as a result of that, we can start to use these to predict. We can use these to make predictions. And those predictions are going to be the fundamental foundation of your assignment next week. Or this week. Tomorrow I will assign it to you. So let me get this all prepped and ready to roll, and then we can get started. So are there any questions? This is from yesterday. So my hope is that if you missed yesterday's class, you watched the lesson. And if you watched the lesson and have questions, hopefully this example will help alleviate some of your misconceptions or understanding issues. Actually, you know what? I'm going to just use a brand new. All righty. So here we have this example question that we will utilize. So just like Mendel from yesterday, we are going to look at the alleles of these pea plants that we worked with. So the allele for a yellow pea plant, is dominant over the allele for a green pea plant. Okay, so the allele of yellow is dominant over green. If a homozygous dominant mother is crossed with a green father, what proportions are expected for the offspring? Now, that was weird. Like a fuzz went in my face. Anyways, so we need to do this step for every single problem that you do in your problem sets. You always start by utilizing a let statement here. So we'll always start by utilizing a let statement here. Can we use capital C and C? Sure, we can use any letters you want. It's entirely up to you. You could use capital FF. You could use capital C and C. we will do capital C and C because Maddie's asked for it. Celestine is here. Bam. Let me just make sure I got everyone. Okay, good. So capital C will represent, so capital C will represent the dominant allele. So capital C will represent the dominant allele. And then what would we use to represent the recessive allele? Lowercase c. Lowercase c. So capital C to represent the dominant allele, lowercase c to represent the recessive allele. So capital C for dominant allele, lowercase c for recessive allele. No worries, Melina. We're just doing the example questions from our lesson yesterday. Okay, so now we need to determine what the genotypes of the parents are. So the genotypes of the parents. So the mother's genotype. Let's look at the mother's genotype. So what is the mother's genotype based on the question above? The mother's genotype based on the question above. If the mother is yellow and homozygous dominant, what is its genotype? Good. Capital C, capital C. Capital C, capital C. The mother is dominant trait when yellow, whereas the father, the father, what's the father going to be if it's green? Closed captions, yeah. If the father is green, yeah, not dominant. It's going to be lowercase c, lowercase c. I'm going to start writing Dominic instead of oops. So mother is dominant allele yellow. Father is recessive green. So mother is homozygous dominant, and I'll add that in here just to homozygous dominant. Homozygous dominant. Oops. Dominic, not dominant. Oops. Dominant. Yeah. Dominant. Oops. What just happened? There we go. And then the father is homozygous recessive, right? Homozygous recessive. No, Maddie, no. Why are you so scared of me, Dominic? You're a scary person. Oh, gosh. Hey, no worries, Joseph. We're just taking up that some of the examples from yesterday. All righty. So we have homozygous dominant mother, homozygous recessive father, yellow mother, yellow father. Now we can use our Punnet square to determine the proportions of those offspring. So let's get to it, folks. We draw our Punnet square as follows. So we put parent one, let's call this parent one the mother. We call parent one. So parent one, oh, sorry, we got to do a cross. We have to say our cross first. We're doing parent one by parent two. You should always, and again, this is always how you should be doing the Punnet square and your problem solving questions. It should follow this exact format, just like in math, right? Mother is crossed with father. And now we're going to add in which parent is which. So parent one is up at the top. Parent one's up at the top. And then parent two down at the bottom. So the alleles of each parent are plugged into here. So parent one, allele one is capital C. Parent two, parent one, allele two, capital C, right? One from each of these Bam, bam. Does everyone understand where those two C's came from? Excellent. Excellent. 3 people get it. 3 people get it. Hopefully more than 3 people get it. Hopefully more than 3 people get it. Oh, geez. Who joined late that I did not get? Joseph is here. Is Daniel here? No, Daniel. No, Christina. Megan and Melina. Melina's here. Alrighty, off it goes. Okay, good. 4 people get it. So that's where those come from. The father's alleles, lowercase c and lowercase c, same thing. Now, here's where the fun begins. Because we are crossing, this lowercase c will be filled in across here, and then this lowercase c will be filled in across here. And it'll go to here and here. So we write this, I'm gonna write this out. This is gonna be a lowercase c, lowercase c, lowercase c, and a lowercase c. And then we do the same thing. We do the same thing with the parent one's alleles. So parent one allele goes here, as well as here. Actually, no, I don't want to put it there. I want to do this like that. There we go. And then same thing said for this. That goes here, then goes there. Good, Joseph. Good. So all of the genotypes are going to be the same. Capital C, lowercase c, capital C, lowercase c, capital C, lowercase c. So if we were to describe the genotypes, oops, how would we describe those genotypes? How would we describe those genotypes? Give me a percentage and a word that we can use to describe these genotypes. Well, are 50% of them going to be CC, or are all of them CC? Yeah, 100% of them, 100% of them. So if all of them are going to have the same genotype, we would say 100% are heterozygous. Capital C, lowercase c. That's what that means. Heterozygous, one of each allele. 100% are heterozygous, or capital C, lowercase c. That's the genotype. What about the phenotype? The phenotype. How can we describe the phenotype of these? So we're looking at every single genotype here to try to understand what the phenotype, or the physical expression of that gene, will be. Good. All of them or just some of them? All of them. So we can say 100% will be yellow. And again, we don't have to use any fancy words here. We're just looking at the genotypes to use that understanding of those genotypes to determine what the phenotypes, or the physical expression, will be. And because every single one of those genotypes has one capital C, at least, we know that that dominant trait will be expressed, and that dominant trait is yellow. But is there like a chance it could be recessive, the phenotype? Well, we'll take a look at that in the next example. Because if you recall, this is our F1 generation. This is our F1 generation. Okay, this is F1. What do you remember about Mendel's F1 generation? What do you remember about Mendel's F1 generation? All of them were the exact same color. No matter how many times he did it, it was all the same color, purple. So let's take a look at what happens in our F2. Let's take a look at what happens in our F2 now. This should be F2. I'll leave that up there for just a second, and then we can, I'll pause my screen, so to speak. Alrighty. Can I move on? There's no questions? You're all talking about F2, so my hope is that you get F1 already in some way. And then worst case scenario, we can go back to the tapes. So here is our F2. We are going to cross that one single plant. We're going to have it self-fertilize. So we cross, oops, I made a mistake there. It should be CC, not CX. There we go. So we're going to cross this now. Parent 1 is the same as parent 2, self-fertilizing, right? Because those pea plants can self-fertilize. And because they can self-fertilize, so we'll call this parent 1, parent 2, it's going to be the same genotype for both parents. And that makes things nice and interesting because this will be a capital C, lowercase c, capital C, lowercase c. And then we do the same thing where we cross that Punnett square. Everything in the same row goes in that row. So we have capital C here, capital C here, lowercase c here, lowercase c here, capital C here, lowercase c, capital C here, and then lowercase c. If you switched it and have lowercase c than capital C, that's fine too. That's fine too. Yeah, Daniel, this is period 2. We're almost done period 2. You got 5 minutes left or so. So what do you notice? Let's talk again about the genotype and phenotype. What do you notice about the genotype? The genotype of this outcome? Well, it has a ratio of 1 to 1. 1 homozygous dominant, 2 heterozygous, 1 homozygous recessive, right? Everyone with me on that one? You see how I got that? I spelled homozygous with an I. Did I? Oh, yes. Bam. Should we not write them in percentages? Well, you could say percentages. That's fine too. You can say 25%, 25% homozygous dominant, 50% heterozygous, and then 25% homozygous recessive. You can do that too. But because we have that ratio is a 1 to 1, 25, 50, 25 as well. That's okay, Daniel, it happens. So that's the genotype, the genotype. Now let's take a look at the phenotype. Oops. So the phenotype, that's where we describe the physical characteristics. And we see it as a 3 to 1 ratio of yellow to green. And lo and behold, it is the exact same ratio that we saw in Mendel's plants, where 3 of the 4 will be the dominant trait, and 1 of that 4 left over will be the recessive trait. On a test, if you ask us for the genotype, would you prefer ratio or percent? It doesn't matter as long as you tell me it in using your words homozygous dominant, heterozygous, homozygous recessive. If you say 1 to 1, 20, 50, 25, or you give me both, you give me all 3, I'm fine with that as long as you give me either a ratio or percentage, as well as using those terms, right? So if it looks something like what I'm doing here, then you're in good shape. Okay? That's mainly what I'm gunning for. It has to look something like this. How do we know which one is which color? Yeah, so remember, if it has at least 1 dominant allele, it will always be that dominant color. So if it has 1 dominant allele, right? So 1 capital C automatically means that it will be yellow. If it has 2, that's fine. It's overkill, but it's still yellow. And if it has no dominant alleles, that means it has recessive alleles only, and it will be that recessive color. All right, let's quickly do this last example. Bam. Brown eyes are dominant to blue eyes. Ah, holy smokes, real life human stuff. Brown eyes are dominant to blue eyes, which makes sense because you would expect to see more brown eyes in the population, which is the case. Huh. And here I am with green eyes. Oh, don't worry, we'll talk about green and everything in between later on. Brown eyes are dominant to blue eyes. What are the expected proportions of offspring, or for offspring, of a cross between two heterozygous parents? So let's let capital B represent the dominant allele. And then we'll let lowercase b represent the recessive allele. You have green eyes, that's cool. Red eyes, oh gosh, here we go. Cool, because the color around my pupils are orange. I think that's bad. So capital B represents dominant allele. Lowercase b represents recessive allele. And we are crossing two heterozygous parents. Heterozygous, meaning we are going to cross capital B lowercase b by capital B lowercase b. Parent 1 by parent 2. All right, let's get after this Punnet square real quick before we run out of time. Pew, pew. All right, parent 1, capital B lowercase b. Parent 2, capital B lowercase b. Here we go. Away we go. Bing. Genotype. Genotype. Again, that ratio of 1 to 1 appears. 1 to 1. 25% homozygous dominant. 50% heterozygous. 25% homozygous recessive. Okay? 1 to 1 ratio. That's not what I wanted. 1 to 1 ratio. Phenotype. Phenotype. The phenotype. If it has one dominant allele, it will be brown. Oops. If it has one dominant allele, it will be brown. One dominant allele there, one dominant allele there, one dominant allele there. No dominant alleles at the last one. So the phenotype, again, that 3 to 1 ratio comes up. 75% will be brown-eyed, 25% blue-eyed. 3 to 1, brown to blue. Nice save, thank you. It's not, I think there's a name for it, is only one BB and the other lowercase b. What do you mean isn't one BB and the other lowercase b, lowercase b? What do you mean by that, Dominic? Before I release everyone to the next class. Like one parent is, no, heterozygous. Heterozygous means one of each. So two heterozygous parents, meaning one parent's heterozygous, the other parent's heterozygous. And if it's heterozygous, you have one of each allele. Yes, Daniel, you missed 90% of the class. Yeah, I highlighted it up there. Two heterozygous parents. Oh, wrong color. But it's called heterochromia. Yeah, that's the thing. We'll talk about heterochromia later. All right, folks, we did it. We got through both examples. So please, 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 please take a look at the homework from yesterday. Take a look at the genetics practice problems in this here as well. You are doing all of this stuff today and tonight for homework because you will need it for tomorrow. You will need it for tomorrow. Class is over. It's period 4 class in 5 minutes. I'll see you all tomorrow for our next lesson, folks. Bye, everyone. Daniel, you missed the class. It's okay. No worries, man. See you later, everybody. Bye. Goodbye, everyone. School's almost done. I know it's amazing. Whee! See you later.